Thank you so much, and thank you all for coming back after lunch. Nice to see you. In this talk I want to tell you about some modules of Equivariant Eilenberg MacLane spectra. And I want to start by kind of setting the stage with some non-equivariant reminders. So in classical homotopy, somehow one of the things that I want to emphasize is that working with cohomology with coefficients in a field, FP, is really nice. So every module over a field is a vector space, and so this cohomology is going to be a graded FP vector space. Okay, and that's not to say that it's easy to compute, but at the very least, all you need to know is where the FPs are, how many copies you've got in any given dimension. And just to emphasize what this means, that means I have a direct sum of shifts of FP. Okay, and this splitting is reflected stably. So what do I mean by that? Well, if I have some module over the Eilenberg MacLane spectrum, HFP, representing this cohomology theory, then I know that that module splits as, well, our direct sum turns into a wedge, and our shifts turn into suspensions, and then we're just getting a wedge of suspensions of HFP itself, right? And so if I wanted to write that maybe a little more precisely, I could say there's some indexing set, and this is a wedge of suspensions of HFP. Okay, and in fact, there's a more general phenomenon. So it's a theorem of Hopkins and Smith. See, I wrote down the date, I think from 1998, that if you have some ring spectrum, well, you're always going to have this nice situation when the homotopy groups of your ring spectrum are a graded field. So this is a graded ring in which every non-zero homogeneous element is invertible. Okay, and then whenever you're in that situation, if you have some module over that ring spectrum, then your module splits as a wedge of suspensions of the ring. Okay, so then, of course, the obvious example that I've given you here is starting with this motivation of, well, you could take your ring to be the Eilenberg MacLane spectrum, representing cohomology with FP coefficients. You could also take your ring, say, to be rational K-theory. That'll give you something a little bit more interesting. So you'll get that these homotopy groups look like Q adjoin the bot class and its inverse. Or the example that I think Hopkins and Smith were most interested in at the time was looking at R given by a Morava K-theory, which we saw in Vesna's talk. And here the homotopy groups, as Vesna told us, well, really you're secretly working at some prime, and then you've got FP adjoin Vn and its inverse. And I think this Vn is in degree 2 times p to the n minus 1. Feel free to correct me if I'm wrong, chromatic folks. But in any case, the point is, well, HFP is really a very special case. This is a field concentrated in degree 0. The homotopy groups are just FP, but you'll get the same kind of phenomenon whenever you work with a graded field. Okay, so I think that's all I wanted to say about the non-equivariant setting, and now I want to make things equivariant. And in fact, for most of my talk, the group is going to be C2, the cyclic group of order 2. And I talked about last time, I want to say yesterday, but I'm not even sure about the days anymore. I think it was yesterday that I told you that any C2 representation, right, any real representation, well, the irreducibles are trivial and sign representations. So I can write this representation V as RPQ, and I'm using the same notation as last time. So I mean by that P minus Q copies of the trivial representation and Q copies of the sign representation. So following this motivic grading convention, so that when I take the 1-point compactification, I get a P sphere, and Q tells me about the twisted dimension or the C2 action on this P-dimensional sphere. Yeah, okay. Okay, so same setup as we had before. Because of these two irreducible representations, we have ROC2 graded cohomology as a bi-graded theory. And I said this bi-graded theory with, say, constant F2 coefficients working in this equivariant analog of F2 coefficients, this constant F2 Mackey functor. Well, this is represented by a genuine equivariant Eilenberg MacLane spectrum that I'll denote HF2 underline. So, well, I think near the end of my last talk, I talked about what this theory gives us when we look at the cohomology of a point. So we take a point with the trivial C2 action in this analog of F2 coefficients. That's really the same as looking at this ROC2 graded homotopy of the Eilenberg MacLane spectrum, representing it, and we get this strangely large ring that I called M2. So again, I'm drawing my bi-graded picture with the topological dimension horizontally and Q, or twisted dimension, vertically. And what we get when we do this computation is we get that copy of F2 in degree 0 along the p-axis. Remember, that was Bredon's integer-graded cohomology theory, and you can form the point with just one zero cell, C2 mod C2, okay? But then away from the p-axis, once we move into the ROC2 grading, we had a lot more. So there are, in fact, infinitely many copies of F2. There are these two cones. There's a little bit of a gap between them, and every lattice point inside the cones is a copy of F2. Okay, and then well, I didn't tell you how to compute this as even as these abelian groups or as an F2 vector space, but I did tell you about the suspension isomorphism that we built into ROC2 graded cohomology, and that's essentially how I would compute this. I would suspend and compute cohomologies of various representation spheres to get this line by line. And then I guess I also like to use Spanier-Whitehead duality to get sort of the flip side of it, but maybe let me just say that if you're interested in how this computation works, I'm happy to talk about it in great detail afterwards, but it is a bit long to say. But this was originally computed in unpublished work of Stong and first appears in a paper by Lewis. And what you get is, well, not only these infinitely many copies of F2, but this upper cone turns out to be polynomial in tau and rho. So this is like tau squared, rho times tau, rho squared, and in fact it's commutative, so tau times rho is rho times tau. There's this gap here, and this class I called theta, and theta is infinitely divisible by rho and tau, so this class theta over tau is meant to mean that there's a class here that when you multiply by tau, you get theta. And if you multiply by tau again, you get 0. And someone reminded me yesterday that theta squared is 0. So theta squared lands here and could potentially be non-zero, but in fact it's 0. And I can't remember what else I wanted to say about this ring, so maybe, I said this last time, but tau is also called U sigma, rho is also called A sigma, and yeah, you'll see both of these kinds of notation. Oh, and I said this last time, but I didn't write it, but tau times theta is 0, and rho times theta is 0 for degree reasons. Okay, so the point I'm really trying to make is remind you of this complicated picture that I haven't quite told you how to compute, but this is very much not a field. In fact, it's a non-Noetherian ring. So the equivariant map from any C2CW complex to a point, crush the whole thing, which maybe isn't isovariant, but is equivariant, as we saw. Well, that's always going to make your ROC2 graded cohomology of your C2CW complex a module over this non-Noetherian ring. And that's not quite what I studied in my algebra course. I don't know about you. I mostly focused on modules over Noetherian rings. So this is very much not a field, and it has a complicated module theory. It has all sorts of strange modules, and you do see these in computations. But then somehow, when you're doing these computations, you run into all sorts of strange M2 modules, and in the end, at the end of your computation, maybe you've got some co-fiber sequence, you run some long exact sequence in cohomology, you compute some differentials, you solve some extension problems, and at the very end, well, it all sews up to just be two kinds of modules. So that was the theorem that I proved in my thesis. So if X is a finite C2CW complex, finite meaning finitely many of these orbit cells, then its cohomology, its ROC2 graded cohomology in this analog of F2 coefficients given by the constant F2 Mackey functor is just a direct sum of shifts. Maybe let me write here representation shifts, because we're working ROG graded, of two kinds of things. So, of course, you need the coefficients. So you need M2, the cohomology of a point. And it turns out the only other piece you need, well, there are infinitely many of these, but they all look quite similar, is the cohomology of all of these antipodal spheres. That's why I included the antipodal sphere as an exercise to think about, because it was an important sphere for me in my thesis. And let me emphasize, there are infinitely many of these, so really for any n greater than or equal to 0. And so this is really infinitely many modules that you see, but they really only come in two flavors. Okay? And by the way, I should say that this is really quite surprising. I think it was unexpected at the time. These computations are fairly complicated, and it's not so obvious, that these other strange M2 modules that you do run into along the way in the computation just kind of seem to sew up and disappear and turn into these two sorts of things. And the story is also much more complicated at odd primes. So this is really a special case at the prime 2. And I should also say this finite is actually quite a strong condition. So even if you have a C2CW complex of finite type, this same sort of structure theorem might not hold. So I have a counterexample with, I think, one orbit cell in every dimension, in fact. So I call this the structure theorem for cohomology. I think Agnes suggested this name, and it's been working for me, so thanks, Agnes. But in any case, we have this splitting, And this is really useful for computations because, okay, you run into some strange M2 module, you know there's going to have to be some kind of differential or some extension problem that's going to resolve it into one of these two kinds of pieces. And that can help a lot. And in fact, helped Christy Hazel compute cohomologies of all the C2 surfaces. Okay, and this splitting, I was able to show that it's reflected stably. So this is really a statement about Eilenberg MacLane spectra. And this says that if Y is a finite C2 CW spectrum, then Y splits, nope, getting ahead of myself. Y smashed with the Eilenberg MacLane spectrum, whose homotopy would compute, say, homology of Y, or let's pretend cohomology, because it turns out they'll basically be equivalent here. So this spectrum, Y smash HF2 underline, splits as a wedge of possibly representations, suspensions of just two kinds of things. Well, of course, you need HF2 underline. If Y was S0, then you would certainly need that. And the other piece is just antipodal spheres smashed with it. Okay. So I don't want to dwell too much on the proof here, but I want to give you an idea of some ingredients that went into the proof. So both of these statements at the cohomology level and at the spectrum level, these used some arguments in bi-graded homotopy. So some of my favorite ingredients are that the ROC2 graded homotopy of this Eilenberg MacLane spectrum, this ring M2 that we saw over there, is in fact self-injective. So by that I mean the regular module as a module over itself. In fact, it is not only projective and free, but it is also injective, which is kind of weird. And the other one that I want to emphasize is this Toda bracket. This was first suggested by Dan Isaacson, and it turned out to be true that the Toda bracket of tau, theta, and rho is equal to 1. And Dan suggested this so in order to help me solve a different problem I was working on, but it helped me solve this structure theorem problem, and so that was very fun. So if you haven't seen Toda brackets before, this is some higher kind of multiplication. I said that tau times theta is 0, and rho times theta is 0. So if I multiply tau, theta, rho, I get 0, but I get 0 in two ways for two reasons. And kind of taking that information and putting it together, I can form a Toda bracket. And if you have seen Toda brackets before, then you know that in fact a Toda bracket should really be a set. And when I write equals here, I mean that there's 0 in a term of C. And so that set has one element, and it is just 1, the unit in the ring. Okay, so give or take, those were the kinds of arguments involved. You know, using that this was self-injective, you could include copies and split them off. And this Toda bracket kind of helped make the arguments that the rest of it was going to look like antipodal spheres smashed with HF2 underline. Okay, and then well, you might want to be able to describe compact HF2 underline modules more generally. And it turns out to do this more general version, you need one more piece. Okay, so with Dan Duggar and Christy Hazel, we showed that if you have some compact module over this Eilenberg MacLane spectrum, for example, C2, CW spectrum smashed with it, but also more, then it splits as a wedge of, again, representation suspensions of, well, of course you need HF2 underline. I said a C2 CW spectrum smashed with it would give you this same sort of thing. So you need that. You, of course, need the antipodal spheres smashed with it. And as I said at first, we hoped that maybe that was it, but it turns out you need one more piece, and that is cofibers of powers of tau, where tau is that element in the homotopy of our Eilenberg MacLane spectrum. So, okay, that was very nice. But what I want to emphasize here is really that what this says is you need three kinds of things. And there are, in fact, infinitely many of them, because I can let n vary, or I can let this power on tau vary. But there are only three kinds. So we have this nice sort of decomposition. Any questions? It is still true that you can interact with questions anytime, even if I forget to ask if there are questions. Oh, maybe I should say one thing before the thing that I'm about to erase, which is that, of course, we don't just get one type of thing, right? This is really not a field, and so this is a quite different story than the non-equivariant case. But I heard a question, I thought.
Which ingredients fail at odd primes?
Which ingredients fail at odd primes? Yeah, so let me come back to that, but let me at least say that these ingredients, so yeah, let me come back to that because I want to tell the story in a certain way, but these ingredients essentially do hold. So the injectivity, I have a terrible argument using graded Bayes criterion, and then John Greenlees told me a phenomenal, very short, beautiful argument. So I know that that's self-injected. And the Toda bracket you can also construct, though it's a little bit more complicated at odd primes. But yeah, it's a little misleading because I've only given you those two ingredients, and they do work at odd primes. Okay. If I haven't answered your question later, then ask again, please, once I get to odd primes. But in any case, back to this C2 story. The point I want to make here is that there are three families of, well, isomorphism classes. Of indecomposables. Okay, and as I said, HF2 underline is very much not a field. And it's not even a PID, it's not a graded PID, but the module theory looks a lot like finitely generated modules over a graded PID. Right, if I talk about indecomposables of Z modules, then there are infinitely many, but I can describe them by their prime powers. Okay, so the proof here, I just want to tell you a little bit about it because I used very different techniques. So as input, we take this theorem of Schweda-Shipley, I think from 2003, which tells us that the homotopy, tells us that modules over this equivariant Eilenberg MacLane spectrum, this category is full and equivalent to chain complexes of modules over this Mackey ring, F2 underline. Okay, and I tried to jump the gun and say, well, so what that tells us is that the homotopy categories are equivalent, which is what we use. Okay, and so what did Dan and Christy and I do? We described the compact objects in the homotopy category on the right-hand side, the derived category of perfect complexes of modules over this constant F2 Mackey functor. Okay, and we did that in a couple of stages. So we classified first the modules over this green functor, F2 underline. There are 5 indecomposables. I guess I should say finite dimensional modules up to isomorphism, but then there are 5 indecomposables. 2 of those are projective. And so perfect complexes are made of finitely many projectives, and so then we use this as input to take these 2 projectives and try to study all of these perfect complexes. And we were able to classify those. So we classified perfect complexes of F2 underline modules using these 2 projectives via a change of basis algorithm. Okay, and well, I haven't told you much about really either kind of proof, but the point I want to make is that it's a really different flavor. It's turning it completely into algebra and working with chain complexes of Mackey functors. And we got this change of basis algorithm. And in fact, what we were able to show, I maybe won't fit there. So let me get a new board. Okay, so what we get is that up to quasi-isomorphism, any perfect complex splits as a direct sum of shifts of, and then we had 4 types of complexes. And I'm going to call these single strands. And I'll say what I mean once I've written them down. But I meant to tell you these Mackey functors. So maybe let me say these 2 projectives. So one of them I'm going to write H, but I just mean constant F2. And we saw its Lewis diagram yesterday. Looked kind of like this. And then the other one I want to use is F. This was the Mackey functor that started with the group ring and took its C2 fixed points and had this diagonal and fold and its group action. Okay, so really explicitly, those are the Mackey functors I'm going to be talking about. Okay, so I take a perfect complex, some big direct sum of copies of H and F, and they all decompose up to quasi-isomorphism into something that looks like a bunch of F's. And these maps, in fact, are all 1 plus twist between them, or F, and then you could tack an H on the end, and there's only one non-trivial map from F to H, so that's the 1 there. Or you could put the H at the beginning. And now, as you might guess, the last kind is, well, you could put an H on both ends. Okay, and when you send these over via this Coulomb equivalence, well, this bunch of copies of F, this is like the Mackey functor you would use if you were building a C2CW complex that had free orbit cells, C2 mod E. And so these are building for you antipodal spheres. Something like this, where you have a bunch of F's with an H at the bottom. This is going to build for you a representation sphere. Maybe that's too many arrows in a row, I don't know. So over here, I'm back in the homotopy category. Here, this gives me the dual representation sphere, so like an S minus N or something. And this last one gives us cofibers of powers of tau. And you might have complained at first, well, this looks like 4 kinds of things. And I said, we got 3 kinds of complexes, but I would call both of these representation suspensions of HF2 underline. So that's kind of how that collapses. Okay? And in fact, what I mean here, oh wait, let me say this first. In fact, we can do this up to isomorphism if we tack on these little contractible complexes where we just have identity maps. And now let me say, what I mean by single strands is that I have a single direct summand in each, at most 1 direct summand in each degree. And at odd primes, you asked what goes wrong at odd primes, and here I can say a little more clearly that that's not true at odd primes. You can't always decompose a perfect complex of the analogous Mackey functors into a single strand. You will sometimes have to have direct sums. Okay, so that's one of the signs that that things change at odd primes. Let me just write that these are contractible, so they're not really giving you much new information. Okay, and then I guess with that, maybe this is a good time to segue into odd primes. So as I said, in fact, in this paper with Jan and Christy, we give an example at odd primes that doesn't decompose in this nice way into a single strand. And so, okay, it looks more complicated, but a lot of things are quite similar. So when G is CP, the cyclic group of prime order P, and P is an odd prime, we get a similar sort of story. So there's an HFP underline that represents ROCP graded cohomology. CP equivariant of CP-CW complexes with constant FP coefficients. And this is no longer bi-graded, though it turns out that, again, thanks to an argument from John Greenlees, that in fact you can boil this down into a bi-graded theory when you're working in such nice coefficients over FP underline. But in any case, we've got this analogous theory, and as I said, I guess I'll call it bi-graded, but maybe I could write ROCP graded homotopy of the Eilenberg MacLane spectrum is self-injective. And in fact, well, there's a toda bracket, decomposition of 1. There are many other similarities. And so for a while, for many years in fact, I was trying to do a similar thing at odd primes. So many things seemed quite similar, and I thought, well, okay, I just need to change what needs to be changed. And as I did that, I found some indecomposables. Okay, so, well, of course you're going to need HFP underline itself. And, well, now the orbit isn't a sphere, the CP orbit, but that's fine. You could take CP plus mashed with HFP underline. There are odd spheres that have a free CP action, so you could take those. And you could take even their even dimensional skeleta and so on. And one thing that's a little bit weird here is not even just is this orbit not a sphere, but you also need something that I would call the egg beater, which I think Mona drew in her talk. This was the one skeleton of the rotating C3 sphere in her example. Okay, but I call this the egg beater because it has like spines and they're rotating. And if you know the term egg beater, that's what that looks like to me. But in any case, so I wrote down lots of indecomposables, and this looked very promising, and then I would always get stuck trying to prove that I had found them all. And then I would find another one, and okay, include this in the list, and then I would always get stuck trying to prove that I found them all. And I really thought it was just, one small thing that was a holdup, because so much of it worked out so similarly. But it turns out I couldn't write them all down because, in fact, it's impossible. So with Jakob Grefstad, a PhD student at NTNU, in work in progress, we show that the classification of compact HFP underline modules is wild. And I mean this in a technical sense. And I hope it's clear. I mean this, for odd primes. That's the board that it's on. But so I mean this in a technical sense. And I will explain a little bit what I mean by that. But morally, it says we really can't write down all these indecomposables. So somehow this theorem here that classified compact HF2 underline modules, well, there were infinitely many indecomposables, but we could really describe them. They came in these families, and we could nicely describe them. And what I mean over here, saying that at odd primes the classification is wild, well, I will tell you morally, and then I will tell you more precisely as well. But morally, this says it's impossible to describe all the indecomposables. And if you know me, you know that I'm quite stubborn. And I was like, okay, sure, it's hard, but that's fine. I'll just keep going, and I will find them all. Well, I can't. I really, really can't, because if you had such a list, it would contain every indecomposable module, and let me emphasize, every indecomposable module of every finite dimensional FP algebra. Okay, so this really, 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 really is a very long list. And if we were working over, say, oh, I guess I can fit more here. If we were working over not a finite field, then there are really even more precise ways to say that this is really an impossible problem. But let's take this as our moral for now, and I will explain a bit more what I mean. But you have maybe heard this term before. So for example, this idea of wild representation type shows up in modular representation theory, where you might be familiar with the fact that the group ring, FP adjoins CP cross CP, is wild unless the prime is 2. Okay, and in a sense, this is a starting point of a lot of modular representation theory, is that, well, you can't possibly hope to describe all the modules, but you can find interesting blocks and so on and so forth. That's not really doing modular representation theory justice, but that's kind of a window to where it begins. Questions so far? Yeah?
So for time 2, the fact that you have complete distribution, is that possible with complete distribution of every indecomposable module of every high dimension F2 item?
No, absolutely not. So F2 algebras, so I gave an example here where this is wild unless the prime is 2, but there are wild algebras over F2. And in fact, I'll explain this a bit more in a moment, but this free algebra on 2 generators, so non-commuting generators, this is also wild. And somehow that's kind of key to the wild case. But no, I'm in no way claiming that we describe all F2 algebras and all of their modules. What I'm saying somehow is that, and I will make this more precise in a moment, is somehow that this homotopy category of HFP underlying modules is really so big. And once you get big enough, well, you contain really too much to describe. And HF2 underlying modules just isn't that big. Good question. Other questions? Okay, well, let me try to make this a little bit more precise, and maybe that will help. So let's let R be a K algebra, where K is a field. Then we say that R has wild representation type. If there exists a functor from the category of modules of, well, I guess I call that one xy, so why not call this xy? The free algebra, take the free algebra, free K algebra and 2 generators, take its module category, and if you can find a functor to your category of R modules that's particularly nice, so it's going to be called a representation embedding. But what I mean by that is a functor reflecting isomorphisms and preserving indecomposables. Well, if you can find such a functor, then we say that R has wild representation type. Okay, and so the idea is that well, if this reflects isomorphisms and preserves indecomposables, then every isomorphism class of indecomposable here will give you an isomorphism class of indecomposable in R mod, okay? Okay, how does that fit in to this moral story? Somehow that doesn't seem to be anything about saying that the representations are describable or not. And so the problem is that that free algebra on 2 generators is doing somehow like a lot of heavy lifting here. So if you have S, some finite dimensional K algebra that looks like K adjoins some generators, mod some relations, then you can always come up with a representation embedding to the free algebra on 2 generators. And now you compose that with your representation embedding to your R module category, and you have just cooked up an isomorphism class of indecomposable in R mod for every isomorphism class of indecomposable in S mod. And you can do this for any such algebra. Okay, so that's what I mean by wild in a more precise sense. That's actually still a little bit of a lie, so let me correct my lie, which is this is what it means to have wild representation type. So, oh, but I haven't told you that part yet, so I will maintain my lie for 1 more minute and then correct it in a moment. This is true what I've said about wild representation type, but how does it relate to our proof? So with Jakob Grestad, we proved that there's this new connection between modular representation theory and equivariant homotopy theory. And we do this really using quiver representations. So we use quiver representations, and I will say a little bit more about that in a moment. But we use them to show that this green functor, FP underline, is in fact representation finite. By which I mean it has finitely many indecomposable modules. But, well, and maybe it's worth saying that there are two projectives. So that part is familiar. But FP underline is in fact derived wild. Okay, and here's where I sort of told you a lie. Not really a lie, but maybe slightly misleading. I told you what it means to have wild representation type, and I didn't tell you what it means to have derived wild representation type. And what I really mean is that the derived category is wild. And so in this situation, our category is representation finite, but derived wild. And I think there are not so many, there's a lot known about representation types of various different algebras in the quiver world, but there is less known about the derived representation type of things. So I think this is also of interest in the algebraic setting. But what I mean by this is that the derived category of perfect complexes of FP underline is wild. And so what we do is we find a strict family of complexes over this free algebra on two generators, where K is FP. And that strict family of complexes does this same kind of thing and shows us that, well, this derived category somehow has an isomorphism class of indecomposable for every isomorphism class of indecomposable of every finite dimensional FP algebra. Okay? And so then somehow a key idea here is that a Mackey functor is a quiver representation. In fact, a Mackey functor is a representation of a bound quiver with relations. And I realized this and tried to Google it, and I found this paper that, or a different paper perhaps. No, I think the paper that I mentioned in my references by Peter Webb. And so this is known to Peter Webb that, in fact, of course, a Mackey functor is a quiver representation. But that really is like the key to bringing these two worlds together. And I will say a little bit about how, depending on the time. Yeah, okay, I think I can. Kind of didn't want to erase what I'm erasing, but oh well. You remember that the prime 2 was good and the non-primes are bad. That's really the upshot here. So let's see. Okay, so what's happening? Why did this work for the prime 2 and not at odd primes? Well, for G is C2, oh yeah, okay. For G is C2, an F2 underline module is a representation of this quiver, this bound quiver with relations. So it has two vertices and two maps. And these are sort of restriction and transfer, but I've done a sneaky little change of basis here. And the relation is that when I compose them, I get 0. So this is an additional relation to the Mackey-Functor relation that we saw before. This is really because it's a co-homological Mackey-Functor, and so this is one extra relation on top of the ones that I wrote down. But in any case, you can kind of boil down the data of an F2 underline module to such a quiver, or a representation of such a bound quiver. I didn't say anything about BA, so BA in general is non-zero. And this quiver corresponds to what's called a gentle algebra. It's just so nice and small and gentle. And gentle algebras are known to be derived tame or derived discrete. And so we do, of course, have infinitely many indecomposables, but they are describable. You can parameterize them. And the way that we did it into these 3 families, or in the algebra world that I just erased, into 4 different kinds of complexes, you can actually see much more easily from this presentation of it. Okay, so this is a little bit more of an answer to what goes wrong at odd primes. Why is it different? When you write down a similar sort of quiver for FP underline, you do not get a gentle algebra. You get something that Jakob is able to show is derived wild. So what happened is I figured out that Mackey-Functors were quiver representations, and someone helped me write down this nice gentle algebra quiver from my Mackey-Functor. I think Sandra Kwama helped me write this down and told me that it was a gentle algebra, and I go and look at the literature and, oh, okay, those are known to be derived tame. And so I gave this seminar that we called PETA, Problems I Think About, and I said, I have this other quiver for this EP case. If you can tell me how to classify all the perfect complexes, then we've got a theorem. We can classify compact HFP underline modules. And a week later, Jakob told me, no, you can't. You really can't. It's wild. So, okay, I want to end by kind of going back to spaces a little bit. So I just want to say that, in fact, we can show that the wildness, this is not a technical term, this is my term, but the wildness comes from spaces. And in fact, to show that there are spaces that realize these chain complexes is not so hard. But what I really mean by this is that they realize them in a particularly, maybe I'll say annoying way, but Jakob and I are working on showing, so this is, again, a theorem in progress, that, in fact, there is no structure theorem for ROCP graded cohomology. With constant FP coefficients. And of course, I mean for P odd. And, oh, I don't really mean for P odd. I mean for P a prime greater than or equal to 7. And I conjecture that also when the prime is 3 or 5, that you also get something wild. But that's TBD, to be determined. Okay, so what I mean is that, well, the wildness comes from spaces, so I can realize these chain complexes as the cellular chain complexes of some spaces with a CP action, but that's not really enough because, for example, FP cohomology in non-equivariant spaces, right, is very easy to describe. May not be easy to compute, but you just know that it's a number of copies of FP. And so it could be that this wildness that we see in this derived wild setting, when you take their cohomologies, they all collapse, right? And what I'm saying is that no, in fact, at least if the prime is greater than or equal to 7, they don't collapse. You get enough families of indecomposables that you cannot possibly hope to describe this. And the argument uses really just a generalization of Hanke's nice argument with the Atiyah-Hertzberg spectral sequence, realizing these as spaces and then making arguments about ROCP graded cohomology. Okay, and then the very last thing I wanted to say is that, in fact, I care about CP because I've been thinking about CP for a long time, but we can do this much more generally. So maybe let me not state the full generality right now, but let me say that this derived wild phenomenon will show us that, in fact, the classification of compact HFP underline modules, oh, that's not how you spell that, classification of compact HFP underline modules is wild basically if G is bigger. So maybe some cases we'd care about in this equivariant world are CP to the N, or maybe CP cross CP some number of times. And in fact, as long as the order of G is greater than 2, then you're going to get something wild. Okay, I don't mean that in full generality. So if your group is C2 cross C3 and you work at the prime 2, then it's not wild, right? But if you work at the prime 3, it is wild. So, but at least in those cases, I'm making an honest statement. Yeah, so it turns out that this FP world is the CP and larger groups world is much more complicated than we expected. And I have some hope that because we've done this non-trivial homotopical lift of modular representation theory, that we can now use genuine equivariant techniques to go back and study maybe some blocks in modular representation theory and see something new. And that remains to be seen, but that's where I'm hoping to go with this. So I will stop there. Thank you.
Thank you very much. Do we have some more questions?
You said several times that this is not a theory, not a theory, but is this true if you look at this as a homotopy group as a graded Tambara functor, or just when you view this with the eyes of ordinary algebra?
So I guess I haven't thought about it enough to give you a complete answer, but I suspect that it can't be a graded field as a graded Tambara functor, only because then its modular theory, like its theory of modules would be like a field.
PID?
But the PID, yeah, that's a good question. I don't know, I haven't thought about it. That would be interesting to find out. It's a good point that maybe there's some richer structure, right, in which this really does look like a PID, and that's what we're seeing the shadow of. So yeah, I would be interested to find out. But somehow I thought the graded Tambara functor was not so interesting for Eilenberg MacLane. I'm looking at Anna Marie. But no, I don't know. Well, anyway, yeah, good question. I will have to think about it.
So I have a question also. You were talking about general groups at the end. So if you're interested in what the underlying coefficient, can you always reduce to the P0 subgroup somehow, these questions? Or can they mix more complicated ways?
I want to say yes. So if the group is abelian and you have a CLOP subgroup of order more than 2, then at that prime that you have that CLOP subgroup, you're going to get wild. And I think we also have something for more general groups, and I wish I had looked this up before I say this now hopefully we're not recording anymore. But I wish I looked this up because I think it's, for more general groups, something about the quotient by the largest normal CLOP subgroup or something like that. Anyway, we can say something slightly more general, and I'm sorry, I don't have it off the top of my head.
Questions? Any online questions?
Actually, I have a question. So are there examples that don't work within just like two groups? Or is it like the odd prime is like the heart of this?
Well, so part of the point I was trying to make here, sorry, and I guess I should have specified my primes more carefully, but like C2 cross C2 is also wild.
Okay.
C4 is also wild. Yeah. I mean, okay, this is all, again, I slightly told a lie. So if you work with C4 equivariant cohomology and you work at F3 coefficients, then it's like a graded field. Then it's very easy. But easy but not interesting, right? But yes, here I really meant for any prime, not just odd primes. Thank you.
Okay, if there are no further questions, we thank Clover again, and then we have